Hi, I'm Susan Terebey from Cal State Los Angeles, and I'm going to tell you about our project to model the outer regions of protoplanetary disks. First, my collaborators are Liz Flores Rivera, a graduate student, Karen Willisey, Andrea Azella, Neil Turner, and Mario Flock. Our motivation for studying the outer disk during the early infall phase are ALMA observations of protoplanetary disks. Substructure in disks such as HL Tau suggests that planet formation is well underway at 1 million years, and implying that planet formation starts even earlier during the protostar phase. At 10⁵ years, gas accretes from the envelope onto the disk and through the disk to the rapidly growing star. Following the gas motions means that we can trace chemical inheritance from the interstellar medium to the disk and to the forming planets. Therefore, we can use ALMA to trace gas motions if we have good theoretical models that include chemistry. We have put together a comprehensive protostar modeling package that we call RadChemT, that stands for Radiation, Chemistry, and Dynamics in Time. We start with an initial collapse model. We add physics, including radiative transfer, chemistry, and dynamics, then use the predicted chemical abundances to produce simulated spectral line cubes that we can form images with and compare with ALMA and CARMA data. To validate the approach, we modeled the class 01 protostar L1527. The schematic on the left shows the inside-out collapse model for the protostar. The protostar is in the center here, size about 0.01 AU. The disk extends north-south, 75 AU radius, extending north-south to match the geometry of L1527. There's an infalling envelope showing gravitational collapse motions, red-shifted, moving due to rotation at the top away from us, and blue-shifted towards us below. In the outer regions of the envelope, there is rotations. It's slowly rotating, but the collapse has not yet reached this outer part. From east to west, there's the outflow. The data show there's a jet in the inner 75 AU, and outside this region, there's a low density outflow cavity. Surrounding the outflow cavity, the data also show that there's an outflow shell moving outwards at about 3 kilometers per second. To determine the temperature, we use radiative transfer, Monte Carlo radiative transfer, using a 3 solar luminosity protostar. We then solve a chemical reaction network to get the molecular abundances, then simulate the spectral line cube to compare with the data. The data here we show are from CARMA, and in green you see the dense H2S gap and N2H plus dense gas, showing the dense envelope. Left to right, Spitzer data 3.6 microns show scattered light from the outflow cavity, and the CO outflow in blue, which appears pinkish here, shows the outflow shell. From the Monte Carlo radiative transfer, we get the temperature, which appears in the top row. The density is shown in the bottom row. From left to right are different zoomed regions for the core, collapsing core, with the smallest scale shown on the left. The protostar here is at the origin. The disk appears in orange, extending upwards. The outflow in blue from left to right, and the envelope in red. Some things to note are that the disk appears wedge-shaped in orange, and that's because we used a ram pressure boundary condition to define the boundary between the disk and the envelope. Also for the temperature, the reddish color indicates temperatures around 100 degrees. This is found in the outflow and the outflow shell, and these temperatures are high enough to drive significant molecular chemistry. Blue corresponds to colder temperatures around 20 to 30 Kelvin, and in the white contour line shows 25 degrees Kelvin. At these cold temperatures, CO freezes out of the gas and onto grains. To illustrate some of the results of the chemistry, we show both predictions for CO and N2H plus and compare with data. In the left panel shows the CO. Down here at the origin is the protostar. From left to right is the outflow cavity, and you see the outflow shell. Black is very little abundance of CO to higher and higher abundance in the outer part of the envelope. The temperatures are so cold that most of the CO has frozen out in the inner envelope. By contrast, N2H plus is expected to be produced when there's little CO, and we see that there's a lot of N2H plus at this time of 10 to the 5 years, and giving the expected anti-correlation that there's little CO in the inner part of the envelope, lots of N2H plus. We take the spectral line cubes that are predicted for N2H plus and produce an integrated intensity map here in the upper right, and you to compare with the data from CARMA in the lower right. The colored emission is CO gas showing the outflow shell. The contours within, draw your attention to the pink oval. The contours there are contours due to N2H plus to compare with the data and the prediction from the model. And we can see that there's extended emission throughout this region. The model predicts in as well as in the data, and moreover, there's a dip in the predicted N2H plus at the position of the protostar in both the model, and the data shows that as well. To study the dynamics, we use C18O. C18O is a good tracer of dense gas in the inner envelope. Here we see the protostar again in this abundance plot, the outflow cavity extending east-west. On this scale, the dashed line shows the disk, which is small. Most of the C18O is near the midplane and is within about 300 AU of the protostar, producing a spectral line cube and generating a position-velocity diagram in a north to south cut through the midplane gives the middle panel that we see here. And on the right is the ALMA data to compare with. Overall, there is a strong similarity between the two. Where the white lines cross is the position of the protostar, both spatially, 0 arc-second offset, and in velocity space at VLSR of 6 kilometers per second. Within the dashed white lines is the region where we expect emission from both the envelope and the disk. And outside the dashed lines then is emission, gravitational motions from just the envelope. We see an overall similarity. We don't actually try to model the gas along the vertical line here in the data. That gas is gas at rest with respect to the protostar and represents gas that's at the outer edge at 10,000 AU from the protostar out at the edge of the system. The gas that we see, the velocities are significantly higher outside, more than 0.5 kilometer per second from the systemic velocity. And they match what is expected through through gravity, both infall and rotational motions. So overall, we find a good match in the similarity in the position velocity diagram. The strength of the C18O emission is also similar to what is seen in the ALMA data. And with further tweaks, we can improve the actual fit. So to summarize, we present the RadChemT package to model protostar dynamics with chemistry and compare with ALMA data. We've included a 2D collapse model, radiative transfer, and chemistry. We generate synthetic images and spectral lines for 292 chemical species simultaneously. Our benchmark study for L1527 validates RadChemT against ALMA and CARMA data, and we find a good match for CO, C18O, and N2H+. More specifically, there is strong CO freezeout and enhanced N2H+ emission at about 1,000 AU from the protostar, and the C18O position-velocity diagram shows striking similarity. Future work is going to focus on including the gas dynamics in the outer disk. Thank you.